Are you feeling stuck because you want to learn Python but you have no idea where to start? Look no further. In this video, we are going to be recreating a two-dimensional model tracking the International Space Center as well as a polar model. You need no experience in Python or any other programming language for this project. Let's hop right in it. So the two applications that I'm going to be using is going to be VS Code. You can use any other IDE that you like, and ChatGPT. Now, you don't have to have the paid version of ChatGPT. You can completely make this whole entire project off of the free version. So there's no excuses. So the first thing that we're going to be doing is opening up Visual Studio Code 3. Once VS Code is open, I'm going to go to the top left corner, click File, and create a new file. And we are going to be using Python. All right, so first things first, I am using my MacBook Pro. You can obviously be using Windows, you could be using Linux. I'm going to be using MacBook, so all my commands are going to be through MacBook. If you want to find the equivalent of these commands in Windows or Linux or any other operating system, it's very simple. You could literally just ChatGPT it, or you can honestly just Google it. So I already have Python installed, but if you don't have Python installed, make sure that you go on python.org/downloads and you could download the latest version of Python for your particular system. But like I said, I already have Python installed. As you could see, I got version 3.12.2. So now that we verified that I have the latest version of Python, I'm going to go ahead and save this file, and I'm going to call it ISS tracker. And I'm going to be saving it to a folder that I've named ISS tracker. Now this folder is completely brand new, it's completely empty. So you want to go ahead and follow this step as well. So now that my file has a name, I'm going to go ahead and create a virtual environment. For that virtual environment, this is going to be the command python-m space VEMV. I'm going to go ahead and run that. Now, in order to activate the virtual environment, I'm going to use this command source space VEMV/bin/activate. As you can see to the left here, in parentheses, you see VEMV, and this indicates that the virtual environment is now activated. Next, let's go ahead to the top left, click File, and let's create a new text file. Now, this new text file is going to be for the dependencies that we're going to need in order to create this project. Now, if you don't know what dependencies are, don't sweat it. Essentially, what dependencies are is they're like libraries or databases, so to speak, that we can pull data from the internet. And we use this data in order to complete our project. But we have to be able to establish a connection with these databases, with these libraries, so that when we run this Python code, it knows where to grab the information from. That's really all these dependencies are. Don't overcomplicate it. So we got NumPy and then Matplotlib. Next, we're going to do Skyfield. Cartopy and PYTZ. And we will go more in depth on what these dependencies actually do later on in the video. So let's go ahead and save this file. We're going to save it as requirements.txt. Make sure that you save it in the same folder that you save your ISS_tracker file. All right, so let's go ahead and switch over to our ISS tracker. And in the terminal, we want to make sure that we are in the correct folder. So for me, I'm going to CD into my desktop. And then from there, I'm going to CD into my ISS tracker folder. Once I'm in there, then I'm going to go ahead and install all of my dependencies using the requirements.txt file that we just created. Once you give it a little while, it should install. Now, if you have any issues with Cartopy specifically, you may need to install Homebrew, and it is very simple to do so. I myself already have Homebrew installed, but it is not difficult at all. So if your Cartopy is not working, your Cartopy dependency is not working, then go ahead and install Homebrew, because that's probably what you're missing. So once that step is complete, all of our dependencies are officially installed and we can get to writing the script. So the first line is going to be a docstring, as you can see here. Now, a docstring is essentially just like a multi-line command, and it's used to describe what the script does. It doesn't really do anything. It's just kind of like a title, like a header, so to speak. All right. Next, let's just go over some instructions. Now, in Python, whenever you use a hashtag, notice here how I started the setup instructions with a hashtag. This is basically like creating a note within your script. All right. So as you can see, it's purple. It's kind of like a grayed out, so to speak, within your script. And so none of this that we're about to write is actually going to be ran, is more for notes. All right. So as you can see here, the setup instructions, it says to run this script successfully, follow these steps. Number 1, make sure Python 3 is installed on your system, which we've already done. Create and activate a virtual environment, which we've already done. Install the required packages by running pip install-r requirements.txt. We've already done. And then lastly, we're going to run the script with Python ISS _ tracker.py, which is our file that we're about to populate right now. Okay. And then below here, you see the required packages, which we've already installed with the requirements.txt file. All right. So let's go ahead and import our first dependency, which is Matplotlib. And Matplotlib is basically just a Python library and is used for creating things like static, animated, and even like interactive visualizations, which is what we're going to be doing in creating these models. Okay. Next up, we have import NumPy as MP. And NumPy is used for handling arrays and mathematical operations. Next, let's go ahead and import matplotlib.pyplot as PLT. And this imports the pyplot module from matplotlib as PLT. This is basically a shorthand to making plots. Okay, so we're going to need this later on. Next, let's import our Skyfield dependency.api. And Skyfield is a main interface for astronomical calculations. We will be using this in tracking the ISS. The load that you see here where it says import load, this is used to load timescales, or TLE, which stands for two-line element files. And the last input that you see there is Earth satellite, and this represents a satellite with Earth-centered orbits. Okay. All right, so next we're going to do Skyfield topless lib, and we're going to import WGS84. Now, in importing WGS84, This is a model for Earth's shape and is used for geodetic latitude and longitudinal positions. Very important. Next, we have Cartopy.crs as CCRS, as well as importing Cartopy.feature as CF feature. Now, Cartopy is a library for geospatial plotting with maps. Okay, and the CRS that you see, the .crs, stands for Coordinate Reference Systems. So CCRS is just kind of like an alias for it. And the dot feature that you see here on line 26, this provides map features like coastlines. All right. Next, we're going to import another Matplotlib, and this is going to be for the animations. Because we're going to be tracking the ISS, we're going to need to animate it to basically make it more visually friendly for us. So this function, which is called func animation, is going to be used to animate the plots frame by frame. And we're going to be able to dictate the frames per second, the different interval levels, and you're going to see that later on. And lastly, we're going to go ahead and import date time. And this date time is going to be a module for working with dates and times. Now, importing the PYTZ, this handles time zone conversions. Now, as you're going to see, the default time zone is going to be UTC, which stands for the Universal Time Zone. However, we here on the East Coast, I'm in Orlando, Florida, we want to get the actual time. I want to use the Eastern Standard Time that I'm using currently in my day-to-day operations. So we're going to need this to be able to do a little converting. All right. So let's hop into the main function. Now, guys, this whole script is really only about 120 lines, depending on, I mean, let's look at it. The first 20 lines aren't even actual code. It's just instructions. So really, you're looking at about 100 lines of code. And it's, like I said, it's nothing extensive. It's nothing crazy. Some of this might be going over your head. But just keep in mind, what we just went over was literally just referencing the libraries, the dependencies that we're going to need to be able to extract data from. That is it. What you just see there from lines 22 or 20 to 29, it's literally just that. All right. So let's go ahead and create our main function. So line 31 is going to be defining our main function. So this is the central function that essentially runs the entire program. All right. DEF is a Python keyword for define a function. Okay. And the parentheses indicate the argument. All right. And the colon starts the function body. So it's important that you have the parentheses, then the colon right after, as that is the syntax for Python. As you do more and more of these projects, you'll just get accustomed to this method. It's just like the English language. You end a sentence with a period. You extend a sentence with a comma. Okay? These are the small little intricacies of Python that are very important, because if you miss one colon, like right there on line 31, if you miss a colon, the whole script, the whole code will not work. However, the overall features of the code are what's more important. Understanding how to communicate to ChatGPT what it is that you want as your end result is much more important. Because at the end of the day, ChatGPT could fix your code grammatically. You know what I'm saying? All right, so let's go ahead and load the TLE data. Now, if you weren't paying attention earlier, TLE stands for two line elements. So we're going to assign the URL of the TLE, the orbital data. We're going to assign the URL of this file to URL. All right. So as you can see, we're defining it. We're creating this variable URL, and we are assigning it to this orbital data file. Now we want to be able to download and parse the TLE data into a list of Earth satellite objects. Remember, we mentioned Earth satellite up here for Skyfield. Okay. The F string that you see here allows inline variable evaluation. The LEN parentheses satellites shows how many satellites were loaded. Okay, so we're going to see this later. When we run this command, it's literally going to print out loaded, and then it's going to give the amount of satellites. Whoops. It's going to give the amount of satellites that were loaded, and then it's going to say satellites. All right, so next, we're going to be able to choose which satellite we actually want to pull from. All right, so we're going to be able to choose the ISS. Now, there are many different satellites, as you can imagine, that you can pull from this URL that you see here. But once again, we want to focus on the ISS. Dictionary comprehension creates a dictionary mapping name to satellite objects. So if you see here, the ISS is named Zarya, and this selects the actual ISS satellite from the dictionary. Next, we have TS is equal to load.timescale. Now, this loads a timescale object, which Skyfield uses for calculating positions over time. So Skyfield calculates these positions automatically for us. Next, what we're going to want to do is we're going to want to create a time range. For those of y'all that did not know, the ISS completes an orbit around the Earth in approximately 90 minutes. Okay, so that's what we're going to be setting it to. So here we see that we're generating a list of time points from 0 all the way to 1 hour and 29 minutes UTC time. Okay, remember I said earlier, the UTC, the universal time, is kind of like the standard, the default time. Because remember, when you're orbiting Earth, let's say you're an astronaut in the ISS, you have to be able to refer to a specific point in time, whether you're talking to somebody in Germany, the United States, or Japan. So this is why it's important that they have a standard time zone. All right. But we want to go ahead and convert that because, like I said, I'm in Orlando. You could change it to whatever you want. You could do PST, you could do mountain time, whatever you want. I myself, I'm going to be converting it to EST. All right. But like I said, this generates a list of time points for approximately 89 minutes. Okay. From 0 all the way to 1 hour and 29 minutes UTC time. All right. So the ts.utc with the parentheses converts into Skyfield time objects. All right. So as you can see here, you got the years 2025. You got the month, which is May. You have the day, which is 3rd. And then you have the range of 0 to 90. All right. Moving on. Now we're going to calculate the satellite positions. So let's start off with creating a variable subpoints. Now, this is going to be used to calculate the point on Earth directly under the satellite at any point in time. All right. The .at parentheses TI computes satellite position at a particular point in time known as TI. Next, the dot subpoint with the empty parentheses gets the Earth's location in latitude and longitudinal form. So with that being said, let's go ahead and define latitude and longitude. So this here, as I said, extracts the latitude and longitude in degrees from each subpoint. Now we're going to go ahead and create an animated ground track. Now this line is going to create a figure and a subplot with a plate carry map projection. Now a plate carry projection, also known as the geographic or equirectangular projection, That's a mouthful. This is a type of cylindrical map projection, all right? And essentially, it's a simple way to represent the spherical Earth on a flat map. This is how we're going to be able to create the 2D model because it's going to be flat. And this is going to use lines of latitude and longitude forming a regular grid. So, as you can see here, the fig size is going to be 12 by 6 in inches. And the subplot KW allows a map projection to be passed on. Like I said, guys, a lot of these things you don't necessarily need to know. You can go more in depth. Like before I did this project, I had no idea what a plant carry is. A plant carry projection was. Okay. And I studied aerospace engineering. Yeah, I just don't know it all. I just don't. So it's okay. It's okay if you don't know it all. But this is why it's important to kind of zoom out, look at the macroscopic view of things, and use the tools that you have at your disposal. Use them to your advantage. Use ChatGPT. All right, so next we're going to set some parameters. So the set underscore global, this sets the map to show the whole entire world. The coastlines obviously draws the world's coastlines, and the grid lines adds grids with labels, longitude and latitude lines. So on line 54, ax.plot is going to plot the entire satellite path. All right, as you can see here, it's calling out longitude. Latitude is going to call out the color, which we're going to color it light blue. And the transform equals ccrs dot geodetic. This indicates that the latitude and longitudinal lines are geodetic coordinates. Geodetic is basically just a form of math that deals with the shape of the Earth, the area of the Earth, or sometimes even just large portions of it. All right, so don't spend too much time trying to decipher that word there. It just means the math that's dealing with the shape of the Earth. So next, we're going to create a red dot. It's going to be known as rho. And it is going to represent the location of the ISS. All right, so this red dot rho is going to be moving throughout our models, both of our models. Now, an important thing to note is that the commas here ensure what's called a tuple unpacking. Now, a tuple is an immutable ordered sequence of elements. It's kind of similar to a list, except it's cemented. Once it's defined, it cannot be changed. And then lastly, on our animated ground track section of our code, we want to display a timestamp. This timestamp is obviously going to follow directly with our sat dot, or the real-time location of the ISS. Notice how we are calling out a transform function again. Now, the transform function essentially applies a function to each element of a data frame or a series, and it returns a new object of the same shape. So this transform equals ax.transaxis places text relative to axis in a range from 0 to 1. Next, let's go ahead and convert our UTC time to Eastern Standard Time. So we're going to define UTC times is going to be equal to the datetime.utc from timestamp. This converts Skyfield time to data time in UTC. Now we're going to convert UTC time to EST time and format it as a string. So as you can see, we got EST equals PYTZ. Now the next part of our code is going to be designated to updating the different frames of our satellite. Now the next part of our code is going to call out each animation frame. So we're going to define it as update frame, in which frame is an index of the current time step. So we're going to have sat dot, which is going to be our red dot that is representing our satellite. And we're going to have set data in parentheses, longitudinal frame, as well as latitudinal frame. This updates the dot position and time text. Then we're going to update the dot position and time text. And we are going to return our sat dot as well as our time text. Next, we're going to call out the parameters of our animation. As you can see, we call out func animation, which animates our plot. And frames is going to be essentially the total number of steps. The interval, we have it set at 500, which is going to be 0.5 seconds per frame. And the last part, blit equals true, essentially optimizes the redrawing of our model. Next, we're going to input a line of code that is going to essentially save our animation as a video using FFmpeg files, as you can see here. And we have the frames per second set at 200. Next, we're going to plot the title of our model, and it's going to be named Animated ISS Ground Track. We are going to also provide it with a legend. So up until this point, we have our two-dimensional model pretty much created, but now we want to show a secondary model using polar coordinates so that we can get a different perspective, a different view of how the ISS is traveling, specifically towards, or not towards, but over our current location. So like I said, me personally, I'm in Orlando, Florida. So I'm going to use the latitude and longitudinal coordinates of Orlando, Florida to input this. You can use whatever coordinates you would like, but we're going to go ahead and create this polar coordinate plot. So the observer is located in Orlando, Florida using the coordinates 28.5383 and negative 81.3792. Next, we are going to get the altitude as well as the azimuth from our location because we are the observer. Now, I'm assuming that most of you know what altitude is. However, azimuth, you might not be familiar with, but here's a little diagram that shows that the azimuth is essentially this angle right here. And the observer's right smack in the middle, and he is observing whether it be a satellite, but the azimuth is this particular angle right here. So we're going to be measuring that as well as the altitude. So a simple math equation to calculate this is going to be difference is going to be equal to satellite minus observer. We're going to define alt as, and it's going to compute the satellite's altitude and azimuth relative to the observer. So we're going to have within brackets difference dot at within the parentheses ti dot alt as within empty parentheses for ti and t. So from here, let's go ahead and define altitude as well as azimuth. So we're going to be able to compute the satellite's altitude and azimuth relative to the observer with these two lines. And then we're going to be able to extract altitude and azimuth angles in degrees using these two lines. Now next, let's convert azimuth to radians and invert altitude for our polar plot. This is going to convert azimuth to radians for our polar plot. And this is going to invert our altitude to plot from center out. So 90 is going to be equal to horizon, and 0 is going to be equal to zenith if you bring up the diagram that I just showed you. All right, and we have reached the final part of our code, and that is going to be to create the animated polar plot. So we're going to create a fig underscore polar and an ax underscore polar. And this line essentially creates our polar plot. Now we're going to define north at top. In a clockwise direction. With a radius limit from 0 to 90 or from zenith to horizon. Then we're going to go ahead and title our polar plot. We're going to call it Animated Polar Sky View of ISS from Orlando. Now remember that we have to initialize our animated path using path underscore line. These coordinates are going to be empty for now. And this path is going to be light blue. And it's going to be labeled the ISS path. And we also have to initialize our animated dot as well. Now, just like the 2D plot, we want to also have a timestamp as well as a date for this polar plot. And these are going to be the positional coordinates for that timestamp, as well as the font size. Now let's go ahead and define our polar animation function. Just as we did for the 2D plot, this animation is constantly being updated. So we're going to have the path line being updated, as well as the dot being updated, as well as the timestamp being updated. And then we return everything. Now we can go ahead and animate the polar view, just as we did with the two-dimensional model using the func animation function. We are sticking to the interval of 500. And once again, same process for the saving of the file at 200 frames per second. And once again, just like the two-dimensional model, let's go ahead and display the actual polar animation. And lastly, putting the finishing touches on our script, we're going to go ahead and ensure that this script is running directly and that it is not imported. And if this is the case, it calls the main function. So let's go ahead and Command S, save our ISS tracker file. And let's go ahead and run this bad boy and see what happens. Boom. As you can see, the red dot represents the ISS. You see the legend on the top right, and then you see the path. You also see the timestamp at the top left. May 4th, 2025, Eastern Standard Time. You also see the title at the top, Animated ISS Ground Track. So this is the actual path that the ISS will be taking in the next 2 days. So today is Sunday, May 4th, and right there it is showing May 5th. So this is the path that it's going to be taking tomorrow. Once you exit out of that, you're going to notice your polar model comes up. The animated polar sky view of ISS from Orlando. As you can see, it is being populated. The timestamp at the bottom is a little fuzzy. I have been having problems with it. If you expand it, you could see it for a second, but then it tends to not want to erase the timestamp, I mean. But other than that, pretty accurate. You see the different degrees along the circumference of the circle. So there you have it, guys. It was extensive. However, if you really break down the amount of Python that you actually had to know to be able to perform and complete this project, it is actually very little. I'm going to show you why. So if you look here, this is my ChatGPT, and you could see at the top where I asked it, hey, I want to create this project. It's a satellite tracker. I want to create a Python program to create two visualizations for satellite tracking. Use online data sources like Celestrak to gather TLE data. Create a 2D visualization of a satellite's ground track. Create a polar coordinate plot of the satellite. And I want to utilize libraries such as Skyfield, NumPy, and Matplotlib. I actually got this project from Angelina Suboy. I hope I'm not butchering her last name. I'm going to go ahead and leave her video down in the description so you guys can see it. I kind of put my own twist to it. I grabbed, her assignment that she kind of challenged her viewers to do. And I added my own twist to it. And I am not a Python expert. She is definitely way more advanced than me. However, we have modern day tools like ChatGPT, and I basically just asked ChatGPT to explain to me and show me everything. Show me how to make it, show me what each line of code means, show me the syntax errors that I might be running into. ChatGPT is your best friend when it comes to this type of stuff. So I just want to encourage you guys that, modern day 2025, we have a plethora of tool sets at our disposal, and there's really no excuse. If you want to learn a programming language, it really comes down to you. How bad do you really want it? You literally have a personalized teacher right in front of you. Do you have a computer? You don't even need a computer. You can actually do this on your phone. You could actually download ChatGPT, download VS Code on your phone, and be able to do this. It's going to be more difficult to do it the mobile way. However, you could still do it. So with that being said, if you guys have any comments, gripes, complaints, any advice that you would like to leave, go ahead and hit the comment section. Hit that like button if you haven't already. Hit that subscribe button as well. If you like projects like this, I'm definitely going to be doing many more. Go ahead and follow my Instagram at Dro Orozco. You can also find me on TikTok, Facebook, all these other social media platforms. I am an engineer at Lockheed Martin. However, I like tinkering with Python programming, ChatGPT on the side. And this was just something that, I had been tinkering with for the last 24 hours. So I just want to go ahead and share with you guys, edify you guys. And that's really it. If you have any other recommendations of any type of projects that you would like to see me conduct and go over, by all means, hit the comment section. All right. God bless you guys in the mighty name of Jesus Christ. I pray that whoever is watching this video, that you encounter God and that you seek God. Because at the end of the day, working out, programming, engineering, your job, your career, whatever, all of that takes a back seat to your relationship with God. So I pray that this video edifies y'all in Jesus' name.